Welcome to this explainer. If you've ever wondered how, say, an aircraft engine runs flawlessly at 30,000 feet without literally tearing itself apart, well, the secret is exactly what we're looking at today. We're going straight to the heart of the modern shop floor to track how a raw, unrefined chunk of metal transforms into a high-precision component. And we'll be looking at the whole process through the lens of metric-driven machining, incredibly strict measurement, and microscopic surface grinding. Let's dive right in. Here's our roadmap for today. First up, machining process techniques. Then, precision measurement using the metric standard. Third, measuring angles with the sine bar. Fourth, surface grinding and finishing. And finally, assessing surface quality. All right, Section 1, machining process techniques. This is all about the geometry of metal removal.
So before a machine even touches the metal, we've got to understand the fundamental divide in shaping techniques, right? We have to distinguish between non-cutting processes, chipless processes like forging, drawing, or extruding, where metal is really just shaped by brute physical force or heat, and cutting processes. Cutting processes, like turning on a lathe, milling, or drilling, actively remove unwanted metal from the workpiece, spitting it out in the form of chips. For our precision journey today, we are hyper-focused on these chip-forming cutting operations.
Now, setting up your cutting tool correctly is absolutely critical for control. You can't just clamp a tool in and start cutting. You actually have to use a tool height gauge to set that tool tip exactly to the dead center height of the lathe axis. It's like a giant geometric puzzle. If you're off by even a fraction of a millimeter, the cutting geometry completely fails, and honestly, your metric tolerances will be ruined right from the very first pass. And that brings us to a foundational best practice on the shop floor. I call it the golden rule of tool setup. Keep your unsupported overhang to an absolute minimum. To ensure rigid stability against those tremendous cutting forces, the overhanging length of the tool should ideally be exactly 1.5 times the tool shank width. Any longer than that, you're going to invite vibration and chatter, which will completely destroy your surface finish and dimensional accuracy. No way around it. Moving on to Section 2, precision measurement, metric standard. It's time for verifying the cut. As the Machinery's Handbook astutely points out, the core of all manufacturing methods starts right at the cutting edge. Improving the control of the machining process isn't just some isolated goal for accuracy. It's actually a major component necessary to achieve a lean chain of manufacturing events. Without rigorous control and precise metric measurement, the whole system breaks down, efficiency falls apart, and waste just takes over. So, how exactly do we measure this? Well, our primary workhorse instrument on the floor is the vernier caliper. This tool is incredibly versatile. It lets a machinist measure outside, inside, and depth dimensions. But the real kicker here is its precision. A standard metric vernier caliper operates down to a staggering 0.02 millimeters of accuracy. To put that into perspective, that's just a tiny fraction of the thickness of a single human hair. And because these tools are so incredibly sensitive, they require strict periodic calibration just to make sure they're telling us the truth. But what happens when 0.02 millimeters just isn't good enough? When we need even tighter metric tolerances, we step it up to the outside micrometer. This relies on a highly precise screw thread principle. Now, using instruments like micrometers requires inspectors who are rigorously trained and certified. Plus, to keep that lean manufacturing chain intact, absolutely strict inspection records have to be kept for every single measurement taken. All right, Section 3. Measuring angles, the sine bar. Let's talk about trigonometry in metal. So we've got our linear metric dimensions locked in, but let's be real, machined parts aren't just simple blocks and cylinders. This introduces a really complex challenge. How do we accurately verify the geometry of a dovetail slide, check the specific radius of an arc, or confirm complex angular dimensions on our freshly machined part? I mean, you can't exactly wrap a micrometer around a corner, right? The answer is this incredibly elegant tool called the sine bar. Instead of giving you a direct readout, the sine bar actually relies on trigonometry. By using flawlessly precise standard gauge blocks to set a specific height, and then combining that with sine bar tables and geometric formulas, a machinist can calculate exact angular coordinates. Think of it like building a perfectly angled ramp. Instead of guessing the slope, you build the stairs underneath it to an exact known metric height. It literally translates the massive headache of measuring an angle into the much simpler task of measuring a metric height. It's pure geometric precision. Which brings us to Section 4, surface grinding and finishing. We are entering the microscopic level. Okay, so The dimensions are verified, the angles are perfect. Now we're transitioning away from macro metal removal, turning and milling tear-away materials super efficiently, but they inevitably leave behind tool marks. So to get that high-class surface finish, we pivot to micro surface finishing processes. We're talking about techniques like lapping and super finishing processes like honing, where an abrasive stick moves with a reciprocating motion against the surface to achieve just absolute ultimate smoothness. This final physical step is all about a fascinating concept called surface integrity. Fun fact, this term was actually coined by Michael Field and John F. Kales way back in 1964. Surface integrity means we aren't just making the part look shiny and pretty. We are literally modifying the material's structural properties by changing its surface condition, usually with an abrasive grinding wheel. The better the finish, the longer the component will survive under intense friction, which is absolutely crucial for preventing catastrophic failures in high-speed machinery. And finally, Section 5, Assessing Surface Quality, the math of perfection. Now that we've ground and honed the surface, we face our final hurdle. To guarantee a truly flawless component, we need a solid way to mathematically assess just how smooth our surface actually is. Improving surface finish follows a really strict procedure. Step 1. We evaluate our target metric roughness lengths. Typically, standards dictate lengths like 0.25, 0.8, or 2.5 millimeters, depending on whether it's a fully machined or non-machined surface. Step 2. We apply our super finishing process, like honing. And Step 3. We meticulously inspect the results using highly sensitive equipment. But what exactly is that equipment calculating behind the scenes? Well, to truly measure surface quality, inspectors definitely don't rely on touch. They rely on hard mathematical formulas. Take the root mean square, or RMS equation, for example. This formula squares the distances of the profile's peaks and valleys, averages them out, and then takes the square root. What that gives us is a hyper-precise mathematical calculation of the deviation left behind by the cut. Another totally critical metric calculation you'll see out there in quality control is RZ. This one calculates the precise mean roughness depth. It does this by taking an average of the highest peaks and the absolute lowest valleys across a defined sampling length. It's a fantastic, foolproof way to ensure that absolutely no rogue scratch is going to come along and ruin a tight mechanical seal. And when graphed out, these geometric calculations visually map out those microscopic peaks and valleys, the H and Y values you can see here, along our predefined metric length, which is represented by the letter L. Whether you're using the peak-to-valley method or the RMS method, this process gives us our absolute final RA value. It acts as the ultimate, indisputable quality check before that component ever gets shipped out the door. So, from rough cutting chips to calculating microscopic peaks and valleys, the journey of a machined part is really one of incredible metric-driven control. But as we look ahead, the forceful trend of industrial microminiaturization isn't just coming, it's already here. Parts are getting smaller, and the demand for absolute, unwavering perfection is only going up. Which leaves us with a pretty provocative question to chew on. As micromachining takes over, just how microscopic will our metric tolerances need to become tomorrow? Thanks so much for joining me for this explainer, and keep exploring the fascinating world of precision.